All right, welcome back. So we know about individual values and types, int, float, stir, and bool values. And we know about the list collection type. A list is a sequence in that you can index items in it from 0 through n-1, where n is the length, or from -1 downward to -n, starting from the back and working toward the front. It's also an iterable, so it can be used, for example, in a for loop to step through all of the items starting from the beginning and going to the end. In this section, we're going to introduce two more collection types in addition to the list that we know about. We're going to introduce the tuple data type, which is very similar to the list, and also the set data type, which behaves very much like a mathematical set, a collection of unique values. All right, so a tuple is like a list, but you define a tuple, or when you display a tuple, it uses parentheses around the sequence of items rather than square brackets as the list does. And a vitally important difference between a tuple and a list is that a tuple is immutable. That is, you cannot change the items within a tuple. So here's an example of creating a tuple. I'm going to say t gets 3, 9, 6, 5, 8, and I've used parentheses to do that. If I ask for the type of t, I'm told that it's a tuple. If I just type t to the shell prompt, the tuple is displayed in parentheses. And I can index the tuple in this, whoops. Okay, now, I hit an enter key by accident, but it's okay because recall that Python allows me to press the enter key and keep going as long as I'm within a pair of parentheses or a pair of square brackets or a pair of curly braces. So now I can type the closing square bracket there, and t sub 0 is the item value 3. T sub 4 is the item value 8. T sub -1 is also the item value 8. So I can index within the tuple just like I can index within a list. I can also, because a tuple is a sequence, I can request a slice. So I can say t sub, let's say 0:2. And that will get me all of the items from item sub 0 up to, but not including, item sub 2. So that's going to give me back a tuple containing a 3 and a 9. Notice that I use square brackets to access items and to access slices just like I do with a list, or for that matter, just like I do with a string. But the result that I get back when I ask for a slice is a tuple, not a list. Because a tuple is immutable, if I attempt to assign a new value, let's redisplay t to remind ourselves what's in there. If I try to assign a new value to one of the items, like t sub 2 gets 123, what I'm attempting to do here is to change this value 6 to the value 123, but I'm going to get yelled at. Tuple does not support item assignment. Well, that's a long-winded way of saying that a tuple is immutable and you cannot change an item in a tuple. All right. So another collection type is the set. And a set is mutable, just as a list is mutable. That is, you can add items to a set, you can remove items from a set. One thing that distinguishes a set from a tuple or a list is that all of the items in a set have to be unique. It's not possible to have duplicate values within a set. And in terms of notation, we use curly braces to contain the items in a set, rather than square brackets as we do for a list or parentheses as we do for a tuple. Now the items in a set are unsorted, although you may be fooled into thinking that they actually are sorted, but I promise you that that's not true. Let me shrink my shell window a little bit here. So I'm going to create a set named S here containing 1, 6, 5, 9, 2, 1, 6, 3. And I've said that items in a set are unique, but in this definition of my set, I've specified 1 twice, and I've specified 6 twice. That's okay. That's not treated as an error. However, only one occurrence of 1 will actually be stored in the set, and only one occurrence of 6 will be stored. So after I've created S, when I display S, you'll notice that there's only one occurrence of 1 and only one occurrence of 6. So the set S contains 6 items, 1, 2, 3, 5, 6, 9. And I can use the type function to confirm that S is referring to a set object. Now, this may look pretty sorted, 1, 2, 3, 5, 6, 9. But that, I assure you, is an accident or a coincidence or something. They are not, you cannot assume that the items in a set are stored in a sorted order. A set, in particular, is not a sequence. There is no concept of the first item or the last item. And so if I try to use square brackets to access, well, let's say the first item, I'm going to get yelled at. A set is not subscriptable. Similarly, I cannot get a slice from a set. Again, because a slice is not, a set is not a sequence. I can use the len function to find out how many items are in the set. All right, so len of S tells me that there are 6 items in the set. And I can use a for loop to step through all of those items. All right, so a set is iterable. I can step through it with a for loop. I can determine how many items it contains using len. But it's not guaranteed what order I'm going to get those set items back in. So here I'm running a for loop, and I've chosen my variable name k. Could have called that apple, doesn't matter. So for k in this set S, for each item in the set, let's print the item, and instead of the new line that we get by default, we're going to display a space character instead. So all of these item values will come out on the same line. All right, and they happen to be displayed 1, 2, 3, 5, 6, 9. That's not anything that the language guarantees. That just happens to be what I got with this set in this shell. There are a bunch of named operations that you can do with sets. Now, because the set has no concept of a first item or a last item, there are no append or insert functions for sets. Append generally implies adding something at the end of a collection. Insert generally implies putting something at the beginning or ahead of some item in a collection. What we have instead for a set is the add method. And if I say add, let's say 8, s.add 8, now I have an 8 in my set. Coincidentally, in this case, the 8 is shown between the 6 and the 9, but that's just, as I said, coincidence. Okay? Now, there are 2 ways I can get rid of items from a set. I can either discard an item or I can remove an item. The difference between discard and remove is that discard is always silent and doesn't fail, even if the item that you're trying to remove from the set doesn't exist. Whereas remove will generate an exception if the item that you're trying to remove doesn't exist in the set. So if I say s dot remove 3, this works fine, and 3 is gone from the set. But if I say s dot remove 0, there is no 0 in the set, and I get yelled at. I get told this is a key error. That is, the unique value 0 isn't found within the set S. On the other hand, if I say s dot discard 0, I don't get yelled at. Now, I guess the theory here is that removing an item from a set that doesn't exist in the set doesn't change the set, so why complain? Okay, so you have your choice between one method, discard, that never complains, and the other method, remove, that will complain if the item you're trying to get rid of doesn't exist. Now, we also have a pop method that will remove and return some arbitrary item from the set. We happen to get 1, but that's not guaranteed. So the 1 is now eliminated from the set and was returned to us. But what returned means, of course, is that I could set up a variable to contain the value from pop, or to refer to the value that has been popped. All right, so some item has been popped from the set by s.pop. So the set S now has one fewer item than it had before, and apparently the 2 was popped, and sure enough, val is referring to 2. Once again, you might look at this and think, oh, I get it. When we do a pop, we're always getting the first item from the set. Well, I'm going to keep repeating myself. No. It's just a coincidence. You can't make any assumptions about which item is being popped from a set. I can get rid of all the items in a set by using the clear method, but I'll just ask you to trust me about that. Also, there's an operator in that I can use. Now, it is a word, I grant you, but it's treated as an operator in the same way that the word is an operator that you can use to detect whether two variable names refer to the same object. Okay, so whereas is compares object IDs, in checks for membership in a set or in a collection. Okay, so for example, I can test whether 9 is in S, and I get true. I can test whether 3 is in S, and I get false. The opposite of in is not in, so I can test whether 3 is not in S, and that is true. Okay, so here are similar examples that you could try out if you would like. One thing I just noticed here on slide 7 that I didn't previously show, let me add, let's say a -3 into the set, and then add 13 into the set. All right, so I've got some more items in here. Notice, I'm so relieved. -3 happens to have been added in such a way that when I display it, it's the last item displayed. So finally, we have an example of the set not having its items stored in ascending order. So that's an accidental demonstration. So that's good, but it's not what I was intending to demonstrate. What I wanted to demonstrate is that if you add an item that already exists, this is not an error. There's already a 6 here in this set. If I add a 6, I don't get yelled at, but nothing happens. If I add a 13, again, I don't get yelled at, but nothing happens. So adding an item to a set where the item already exists in the set is not considered an error. Okay. Now, there are also a variety of set versus set comparisons and operations. These methods that we looked at here on slide 6 all have to do with adding or removing or checking for individual values within one set. But often we want to compare two different sets to each other to see what the intersection of the two sets is, or what the union of the two sets is, and so on. So here are these named operations where we have a current set on the left-hand side, and then we have some method name, and then we have an entire set as the argument to that method. All right, so I'd better create myself another set here. So let me create S2 to contain 5, 6, 7, 12, 13, 15. All right, so S is 5, 6, 8, 9, 13, minus 3. S2 is 5, 6, 7, 12, 13, 15. And if I ask for S dot difference S2, now the difference is the items that are in S1 that are not found in S2. Okay, so here are all of the items in S. Here are the items that are in S2, and we notice that 5, 6, and 13 are in S2. So if we eliminate those items from S that are in S2, that are also in S2, what we're going to have left is 8, 9, and minus 3. So that is the set difference. All right, so the 8, 9, and minus 3 are the items in S that are not found in S2. I can go the other direction. I can ask for the items in S2 that are not also in S, and I get 12, 7, and 15. And to my very great pleasure, notice that these are also not in ascending order. So we've seen some examples now where the items in the set are not displayed in ascending order. The symmetrics difference of two sets is the items that are in one set or in the other set, but not in both sets. All right, so let's remind ourselves. Here's what S contains. Here's what S2 contains. And if I say S dot symmetric difference, okay, amazing, I typed it correctly. Symmetrics difference. What I'm going to get now is the set of things that are in S but not S2, together with the items that are in S2 but not S. So in other words, in mathematical notation, what I'm getting is the union of the items in S1 that are not in S2, together with the items in S2 that are not in S1. All right, next up we have intersection, which gives us, in mathematical notation, the intersection of the two sets. That is the items that are in both. So here I'm going to say S dot intersection S2. Okay, 13, 5, and 6, as we've seen. 13, 5, and, well, 13, 5, and 6 are in S and also in S2. So those are the intersection of the two sets. I can ask whether the two sets are disjoint. In this case, of course, they are not disjoint. So if I ask whether S is disjoint with S2, I get false, because they do contain items in common. If I were to ask whether S is disjoint, and let me just make up a set, -1, -7, -33, 1000. Those two sets, S and this literal set, -1, -7, -33, 1000, have no elements in common, and so they are disjoint. I can ask whether one set is a subset of another or a superset of another, and I can ask for the union of the two sets. So here's S, here's S1, whoops, sorry, here's S, here's S2, and S dot union of S2, or with S2, gives me 9 items that are either in S or in S2 or both. Okay, and so these illustrations here on slide 10 are similar to the ones that I have done interactively. You can try these out if you'd like. Rather than using these lengthy names, intersection, union, symmetric difference, and so on, there are several symbols that we can use instead for some, but not all, of these set versus set operations. For example, here's S, here's S2, and if I ask for S minus S2, that is the difference. It's the same as saying S dot difference S2, and what I get are the items in S that are not found in S2. Other way around, S2 minus S is the items that are in S2 that are not in S. The symmetric difference uses a symbol called the exclusive OR symbol. S exclusive OR S2 is the union of these two symmetric differences. Pardon me. The symmetric difference is the union of the two differences. All right, so this is all of the items that are in S but not S2, or that are in S2 but not S itself. Intersection is the ampersand symbol. Here's S, here's S2. S intersect S2 is going to be 5, 6, 13. Well, here shown in a different order. And then union uses the vertical bar symbol. And if you have experience with other languages at all, you may recognize the vertical bar symbol as being the so-called bitwise OR symbol. And the ampersand is the bitwise and the caret symbol, or the hat symbol, is the bitwise exclusive OR. So those symbols are overloaded, is the correct term there, to work with sets in Python, as well as with patterns of bits stored in integers. Okie doke. All right, and so here on slide 12 are similar examples to the ones that I've gone through interactively myself. Now, as far as what you can put into a set, it turns out you're restricted to putting what are called hashable items. And a complete definition of what hashable means is a little bit beyond the level of understanding that we have so far, but we can describe things that are hashable. Any value that is one of the basic data types or the special value none, these things are all hashable. And immutable objects containing hashable items are also hashable. So a tuple is also hashable if and only if all of the items that the tuple contains is hashable or are hashable. Now, because a list is mutable and a set is mutable, meaning that the items within a list or the items within a set can be changed, these things cannot be stored in a set. So you can't have a set of lists, you can't have a set of sets. But here, we're creating a list, we're creating a set, S3, containing an int value 5, a float value 4.7, the special value none. Then we have a tuple containing 2 one-character strings. Strs are hashable. They are one of the low-level types. And here I have the string hello and the Boolean value true. So all of these things are hashable, and so I can create a set of them. When I display S3, notice that the values come out in an entirely different order, but they are the same values that I put in S3. Also notice that the order is different from what I got when I wrote the course notes here. There's no guarantee about how your shell is going to arrange to represent and display the items within a set. So the version of S3 shown on slide 13 and the version of S3 shown here are equivalent to one another. The values are being displayed in a different order is all. All right, so that gets us to the conclusion of this material about tuples and sets. And in Lab 3.3, you'll have a chance to do some experimentation with these things.